Good morning, everyone. I am Garima from BSc Chemistry Honors first year. Today, we are going to start our chapter from Organic Chemistry. The chapter is Steriochemistry of Organic Compounds. Introduction. The molecular structure of compounds plays a very important role in the study of organic chemistry. During this study, one comes across many instances where a given molecular formula represents two or more compounds having different properties. This is evidently due to some differences in molecular structure of these compounds. Such structures which have the same molecular formula but different properties are known as isomers, and the phenomena is known as isomerism. Isomerism. The concept of isomerism is an important feature of the study of organic compounds. It relates to the existence of different compounds which have the same molecular formula but different properties. Such compounds are called isomers. Iso means same, mers means parts. The difference in the properties of isomers is due to the difference in the relative arrangement of atoms in their molecules. There are two types of isomers. First, structural isomers, merism. Second, space or stereoisomerism. Structural isomerism. This is the type of isomerism which is due to the difference in the arrangement of atoms within the molecules having the same molecular formula. The student is already familiar with the various type of structural isomerism. However, we shall present here a brief review for the sake of recapitulation. First, chain or nuclear isomerism. This is a kind of isomerism which arises when the compounds having the same molecular formula differs only in the arrangement of carbon atom in the chain. Thus, normal butane or isobutane having same molecular formula C4H10 represent two chain isomerism, that is N-butane, isobutane. Similarly, there are three chain isomers having the molecular formula C5H12, N-pentane, isopentane, neopentane. Positive isomerism. If two or more compounds with the same molecular formula but differ positions occupy by a characteristic atom or group attached to the carbon, position isomerism is said to exist. N-propyl chlorine and isopropyl chlorine afford an understanding example of this type of isomerism. Both these compounds have the same molecular formula C3H7Cl, the same carbon skeleton, but differ from each other in the position of attachment of chlorine atom. N-propyl chloride, isopropyl chloride. Similarly, there are two butenes which differ in the position of double bond in the molecule. But 1 in, but 2 in. Functional isomerism. This type of isomerism is due to the presence of different functional groups in compounds having the same molecular formula. For instance, C2H6 represent two compounds, ethyl alcohol, dimethyl ether. These two compounds have entirely different chemical and physical properties because of the presence of different characteristics group. Acetone and propionaldehyde represent another pair of compounds exhibiting functional isomerism. Here the structure of both are given. Metamerism. This type of isomerism is due to the difference in the distribution of carbon atom on either side of functional group in compounds having the same molecular formula. For instance, diethyl ether and methyl propyl ether represent a pair of metamers having the molecular formula C4H10O. Diethyl ether methyl propyl ether structures is given. Diethyl ketone and methyl propyl ketone having the molecular formula C5H10O furnishes another case of metamers. Diethyl ketone and metapropyl ketone structures are given here. Ring chain isomerism. This is a type of isomerism in which two compounds having the same molecular formula have open chain and ring structures respectively. For example, propene and cyclopropane having the molecular formula C3H6 afford a simple example of ring chain isomerism. Propene, cyclopropane. Similarly, but1-ine and cyclobutene are also ring chain isomers of each other. But1-ine and cyclobutene structures are given here. Tautomerism. This is a special type of functional isomerism where the isomers exist simultaneously in dynamic equilibrium with each other. The isomers which are involved in equilibrium are known as tautomers. The structure of tautomers generally differs from each other in the point of attachment of one of the atom in the molecule. In keto-enol tautomerism, which is the most important type of tautomerism, the tautomers differ from each other in the point of attachment of a hydrogen. Thus, acetyl acetone exists as a tautomerism mixture of two forms, the keto form and the enol form, which differs in the point of attachment of the hydrogen as shown below. Keto form of acetyl acetone is given on the left hand side, where enolic form of acetyl acetone is given on the right hand side. Similarly, ethyl acetate exists as a mixture of keto and enolic form. Here the structures of both are given, keto form and enolic form. Tautomerism versus resonance. It will be quite appropriate at this stage to distinguish between the phenomena of tautomerism and resonance. It may be noted that tautomerism is marked by the existence of distinct structure which differs mainly in the point of attachment of the atom in the molecule. On the other hand, in case of resonance, the different contributing structures have the same arrangement of atoms. Third, the tautomers are distinct compounds which are actually known to exist and which may even be isolated in certain cases. On the other hand, in resonance, contributing structure do not exist as such. There are written only to have an idea of the structure of resonance hybrid, as this structure cannot be represented in the terms of valence bond method of representation. Stereoisomerism. This is a type of isomerism which arises due to the difference in the arrangement of atom in space. Its study is known as stereochemistry. In this unit, we shall discuss the important aspects of stereochemistry, stereoisomers. Stereoisomerism. The isomeric compounds which differ from each other only in the relative arrangement of atoms in space but resemble one another with respect to which atoms are linked to which other atoms are called stereoisomers, and the phenomena is known as stereoisomerism. There are three types of stereoisomerism: optical isomerism, geometrical isomerism, conformational isomerism. Before proceeding further, it may be pointed out that the different structures of conformational isomers of a structure are not superimposable on one another but are easily interconverted into one another by rotation around single bond. In contrast to this, the different structures of optical or geometrical isomers are non-superimposable on each one another, and at this time they cannot be interconverted except by breaking and making of bond. For this reason, optical and geometrical isomers are also collectively known as conformational isomers. While conformational isomers of a substance exist only as a mixture of different forms, the conformational isomers can be prepared as distinct individual substances. For difference between conformational and configuration, please refer to section 2.20. We shall now discuss the different types of stereoisomerism, stating with optical isomerism. Optical isomerism. This is a type of stereoisomerism in which the isomeric compound resemble one another in their chemical reactions and most of the physical properties but differs in their effect on polarized light. We shall now first review some fundamental terms concerning optical isomer and then discuss other features of optical isomerism. Tetrahedral concept of carbon. This is well known that in methane and all other compounds having a carbon bond to four other atoms or group by single bonds, the four bonds of carbon are directly towards the four corners of a tetrahedron. The tetrahedron concept of carbon put forward by Liebel and Wentz-Hoffe is very helpful in understanding the phenomena of optical isomers. A representation of the tetrahedral carbon atom is shown in figure 2.1a by molecular model and in figure 2.1b by wedged formula. Representation of tetrahedral carbon is shown in figure 2.1. It should be noted that by convention, the wedge represent the bond pointing towards the observer out of the plane of the paper. The hatched line or dashed line represent the bond behind the plane of the paper. The normal line shows the bond in the plane of the paper. Polarized light. A ordinary ray of light consists of electromagnetic waves of various wavelength and its vibration takes place in all planes at right angle to the direction in which it travels. A ray of light which consists of waves having only one wavelength is known as monochromatic light. Even such a ray have its vibration in all planes. However, if a ray of monochromatic light such as yellow light from a sodium flame is passed through a nickel prism, a special prism made from calcite, which is a particular crystalline form of calcium carbonate. The wave motion of emergetic light is restricted to only one plane. Light which vibration takes place in only one plane is known as plane polarized light or just polarized light. The plane along which vibration takes place is known as plane of polarization, and the nickel prism used for polarizing the light is known as polarizer. This figure shows the vibration in ordinary polarized form of light. Optical activity. There are certain substances which can rotate the plane of polarized light. For instance, when polarized light vibrates in a certain plane is passed through cane sugar solution, the light which emerges out vibrates in a different plane. Such substances which can rotate the plane of polarized light are said to be optical active, and the property is called optical activity. The substances which rotate the plane of polarized light towards the right are termed dextrorotatory, while those which rotates towards the left is called levorotatory. The instrument used for measuring the angle of rotation, denoted as alpha, of the plane of polarized light is known as polarimeter. The angle of rotation through which plane of polarized light is rotated by an optical active substance depends upon many factors, which are nature of the compounds, length of the liquid column through which the light passes, concentration of the solution and nature of the solvent in case of solid substance only, temperature, wavelength of light used. Specific rotation. In order to compare the rotatory power of different substances, optical activity is expressed as specific rotation. If the angle of rotation of the plane of polarized light passes by a tube on 1 decimeter 10 centimeter in length filled with a solution having 1 gram of the substance per ml of the solution at the temperature T using light of wavelength 5893 angstrom from sodium vapor lamp. This light is called D line of sodium. Specific rotation is generally calculated from the equation specific rotation is equal to observed angle of rotation divided by L into D, where D represents the weight in grams of solute in 1 ml of solution or density of the solution if it is a liquid, and L is the length in decimeter of the tube filled with the sample. For instance, the specific rotation of a cane sugar solution at 293 Kelvin is 66.5 degree 293 D. Element of symmetry. The phenomena of optical activity is essentially related to lack of symmetry in molecular structure. A simple method to decide whether a molecule is symmetrical or not involves three criteria of symmetry known as element of symmetry. An element of symmetry may be defined as the plane, line, or point with respect to which the structure possesses a definite symmetry. There are three elements of symmetry as discussed below. Plane of symmetry. It is an imaginary plane passing through an object or a substance structure which divides the object or structure in two halves such that one half is the mirror image of the other. For example, a beaker has a plane of symmetry as shown in figure 2.3a. Similarly, the molecule of propanoic acid has a plane of symmetry as shown in figure 2.3b. Here this figure shows A. Plane of symmetry in a beaker, B. Plane of symmetry in propanoic acid. Second, center of symmetry. It is an imaginary point within a molecule at which all the straight lines joining identical points in the molecule crosses each other. For example, the center of symmetry in the molecule of 2,4-dimethyl cyclobutane 1,3-dicarboxylic acid is shown below in figure 2.5. It may be noted that a structure can have more than one plane of symmetry, but no structure can have more than one center of symmetry. Axis of symmetry. It is an imaginary line passing through the molecule so that when the molecule is rotated about this line, exactly similar geometrical arrangement appear more than once in one complete rotation, that is in a rotation through 360 degree. If the identical arrangement appear twice in one complete rotation after every 180 degree, the axis is called two-fold axis of symmetry, denoted as C2 axis. If the similar arrangement appear thrice, it is a threefold axis of symmetry, and so on. For example, trans 1,2 dibromocyclopropane possesses as C2 axis of symmetry in the plane of the ring which bisects the bond between carbon atom 1 and 2 and intersects the carbon atom 3 as shown in figure 2.6. When rotated about the axis, the same arrangements appear after every 180 degree. Alternating axis of symmetry or rotation reflection axis. This is another element of symmetry which is rarely used. A molecule is said to have an n-fold alternating axis of symmetry if rotation of an angle or by 360 by and about the axis formed by reflection in the plane perpendicular to this axis gives a molecule which cannot be distinguished from the original molecule. For example, 1,3-diethyl 2,4-dimethyl cyclobutane possesses a two-fold axis of symmetry as shown below. If the molecule A is rotated by an angle of 180 degree, that is 360 by 2, about the axis S2, which passes through the center of the ring. It gives a molecule B. The reflection of B in the plane perpendicular to the axis gives the original molecule A. A gives rotation by 180 degree, 360 by 2, about S2 will give B. Then reflection is plane perpendicular to S2 will give C. It may be noted that a one-fold alternating axis of symmetry correspond to the plane of symmetry, while a two-fold alternating axis of symmetry correspond to center of symmetry. Molecular chirality, chiral and achiral structure. Chiral structure. A structure or object is said to be chiral or dissymmetric if it is not superimposable on its mirror image. Such a structure does not have either a plane or a center of symmetry. The most perfect example of chiral object is human being. It does not have any plane of symmetry and cannot be superimposable on its mirror image. If you hold your left hand up to a mirror, the image looks like a right hand, but if you try to superimpose one hand over the other, both palms down, you cannot do it. Similarly, a right handed glove and a left handed glove are chiral objects. A very large number of organic molecules such as 2-chlorobutane and lactic acid are known as chiral substances as they are not superimposable on the mirror image. This figure shows non-superimposable mirror images. The structure having chiral substructures are said to possess the property of chirality. It should be noted that chirality is the property of complete objects or structures and not of its parts. It may be noted that even though there are three kinds of element of symmetry, chirality is primarily related to lack of plane of symmetry and the center of symmetry. Second, achiral structure. A structure or object which have a plane of symmetry and is superimposable on its mirror image is known as achiral or symmetrical. Such a structure always possesses a plane of symmetry or a center of symmetry. For example, the letter A and the button on your shirt represent achiral structure on object. It can be easily seen that each of these have a plane of symmetry and is superimposable on its mirror image. This figure shows achiral structures. Third, origin of chirality in organic compounds. Most of the organic compounds which are chiral in nature owe their chirality to the presence of a carbon atom bounded to four different groups. Such an carbon is termed as chiral carbon or chiral center or stereogenic center or stereocenter, earlier known as asymmetric carbon. A stereogenic center or chiral center or chiral carbon is a carbon atom which is bonded to four different monovalent atoms or groups such as CABCD. There can be two different tetrahedral models for CABCD, which differ in the spectral arrangements of various groups attached to carbon, as shown in figure 2.9, shows non-superimposable mirror images model of CABCD. Each of the two models is related to the other like a object to its mirror image, and one cannot be superimposed on the other no matter how we turn or twist them. Each of these models, however, represent a chiral structure. Optical isomerism. In enantiomers, it has been observed that optically active substances always exist in two or more isomeric form which differs with respect to their optical activity or their action on plane polarized light. As already stated, the isomer which resemble one another in their chemical reaction and most of the physical properties but differs in their effect on polarized light are called optical isomers, and the phenomena is known as optical isomerism. There are two main types of optical isomerism. These are enantiomer diestereoisomer. We shall now discuss these type of, starting with enantiomer. Enantiomer, it is the simple kind of optical isomer which are discovered by Pasteur in 1848 as a result of his work on the salts of tartaric acid. He observed that optically active sodium ammonium tartrate consists of a mixture of two distinguished type of crystals. These two type of crystals were not superimposable on each other, although their shapes were like mirror images of each other. The relationship between the two distinct type of crystals. These two types of crystals were not superimposable on each other, although their shapes were like mirror images of each other. The relationship between two types of crystals may be compared to that between a pair of right and left-handed gloves. Pasteur separated the two types of crystal from the original sample with the help of a magnifying lens and a pair of tweezers. Unlike the original optically inactive sample, each type of crystal were found to be optical active in their aqueous solution. Moreover, the specific rotation of the solution of one type of crystal was found to be equal but of opposite sign to that of the solution of second type of crystal. Considering the fact that difference in optical rotation was observed in solution where the solute exists in form of simple molecule, Pasteur proposed that the molecules consisting the two type of crystals are were not superimposable mirror images of each other. Such isomers whose molecular structures are not non-superimposable mirror images of each other and which rotate the plane polarizing light equally but in opposite direction are now known as isomerism and enantiomer, or enantiomorphs. The phenomena of mirror images isomerism is known as enantiomerism. Since the mirror image isomerism differ only in a spectral arrangement of atoms, enantiomer represent a type of stereoisomer. Explanation of stereoisomerism. The existence of mirror images isomerism or enantiomer was justified by events on the basis of tetrahedral concept of carbon atom. Let us try to apply this concept of an imaginary compound of the type CABCD in which a carbon atom is attached to four different groups. Such a compound can be represented by two different tetrahedral models which differs in the spectral arrangement of various groups attached to the carbon atom. The two models are related to each other like an object or and its mirror image, and one cannot be superimposed over the other. No matter how we turn or twist them, these models represent the enantiomers of the compound. For example, let us draw tetrahedral formula of enantiomer form of substances such as lactic acid and 2-methyl 1-butanol, which are known to exist enantiomers. In each of these cases, we find that it is possible to construct two formula which are non-superimposable mirror images of each other, and as such they are represent the different enantiomer. It may be pointed out, however, if the compound containing a tetrahedral carbon atom does not have four different groups attached to this carbon, then the molecules are superimposable on their mirror images. This is illustrated below with the help of bromochloromethane. Such compounds do not exhibit enantiomer because of all their molecules are of the same type. This figure shows no enantiomerism possible as mirror image of bromochloromethane are superimposable. Representation of stereoisomers. First, flying wheel formula. We have so far used the molecular model and three-dimensional tetrahedral formula to represent the stereoisomers. The tetrahedral formula can also be drawn in a somewhat different but more convenient way known as flying wedge formula. For drawing these formula, the molecule is oriented in space in such a way that two bonds of the stereo center points towards the observer while the other two bonds are directed away from the observer. The bonds pointing towards the observer are represented by wedged drawn horizontally, which may or may not be drawn along the straight line. The bonds pointing away from the observer are represented by hatched or dotted line drawn vertically. For example, the molecular model tetrahedral formula and wedged formula of one of the enantiomer of lactic acid may be shown as follows. These shows the molecular tetrahedral and flying wheel formula. Similarly, the three kind of representation of the other enantiomer of lactic acid can be shown as below. Tetrahedral flying wheel formula of enantiomers of 2-butanol are given below. Planar representation of three-dimension formula. Fisher projection formula. The use of molecular model is no doubt the most suitable method of showing the spectral orientation of atom constituting the molecule, but it is not very convenient to represent the formula of compound on paper. Therefore, a simple although not foolproof method was introduced by Emil Fischer 1891 for projecting three-dimensional formula of chiral molecules on planar surface. The planar representation are called Fisher projection formula. Procedure for writing Fisher projection. For writing the projection formula, the following procedure is adopted. The chiral molecule is viewed in such a way that two groups beyond two chiral carbon points towards the observer while the other two groups point away from the observer. Second, the various groups attached to the chiral carbon are then projected to the plane of the paper in the form of a cross so that horizontal line represent bond pointing towards the observer while vertical line represent the bond pointing away from the observer. If the chiral molecule containing two or more chiral carbon, each carbon is considered separately as discussed above. The vertical part of the projection formula should represent as so far as possible the longest chain of carbon atom in the molecule with the carbon atom to a number as 1 according to IPSC system bringing right written at the top. Fourth, chiral carbon atom is not written at all while writing the projecting formula. It is taken for granted that the chiral carbon atom is located where the horizontal and vertical line cross each other. For instance, the projection formula of the two enantiomer of lactic acid may be represented as shown below. This figure shows the projection formula of two enantiomer of lactic acid. Chiral and achiral molecules with two stereogenic center diisomerism. We have learned that a compound containing one stereogenic center exists in two stereoisomerism form which are known as enantiomers of each other. What about compound containing two stereogenic center? Quite expectedly, such structures can exist in more than two stereoisomeric form. To illustrate this statement, let us consider the case of 2,3-dichloropentane which contain two stereogenic centers. Since the four different groups attached to one stereogenic center are not the same as those attached to the other, the two chiral carbon atoms are dissimilar for the another. There are as many as four stereoisomerism possible for this compound. These figures show one pair of enantiomer and second pair of enantiomers. Explanation of Formula 1 and 2 reveals that they are non-superimposable mirror images of each other, hence represent a pair of enantiomers. Similarly, 3 and 4 are also non-superimposable mirror images of each other and as such represent another pair of enantiomers. Let us now compare the Formula 1 with the Formula 3. It becomes immediately clear that the two formula have identical conformation about one chiral carbon but mirror image conformation about the other chiral carbon. The net result is that the two forms are neither identical nor mirror images of each other. Such stereoisomers of a substance which are not mirror images of each other are known as diastereomers. In addition to Formula 1 and 3, Formula 1 and 4, 2 and 3, 2 and 4 are also represent pair of diastereomers. Fisher projection formula and flywheel representation of four stereoisomers of 2,3 dichloropentane are given below. Fisher projection formula is given here. This figure shows flywheel representation. Erythro and threoisomers. A special system of nomenclature is sometimes used for distinguishing between diastereomers in which two of the atoms or groups attached to one stereogenic center are the same as the two atoms or groups attached to the other stereogenic center. This method is derived from the names of two diastereomeric carbohydrates, erythros in which similar groups are on the same side and threos in which similar groups are on the opposite sides as shown in the figure. If the two similar groups are on the same side in the Fisher projection formula of the molecule, the diastereomers is known as erythroisomer. If the two similar groups are on the opposite side in the projection formula of the molecule, the diastereomers are known as threoisomers. For example, of the four isomer of 3 chloro 2 butanol, one pair of enantiomer is known as Aristro, while the other pair of enantiomer, which are diastereomers of the first pair, is known as threo as illustrated below. It may be seen that any one compounds of one pair is diastereomer of any one compound of the other pair. The name Aristro and Threo are derived from the name of two simple sugar, aristros and threos, having the following conformation. Meso compounds. Let us now consider a compound containing two similar chiral centers having the same set of four different groups attached to each other of the chiral carbon atom. A typical example of such a compound is produced by tartaric acid. In views of the fact that it has two chiral center, one may expect the existence of four stereoisomers of this acid having the configuration 9, 10, 11 and 12. This figure shows the pair of enantiomer 9 and 10, 11, 12 shows superimposable mirror images representing only one compound. Formula 9 and 10 are non-superimposable mirror images of each other and therefore represent a pair of optically active enantiomer. Formula 11 and 12 again have a mirror image relationship. Close examination of these formula, however, shows that one of these structures may be superimposed on the other, just as rotating it through 180 degrees within the plane of the paper. These two formula therefore represent two superimposable mirror images formula of the same compound. Further examination of formula 11 or 12 reveals that in spite of two chiral centers in it, the molecules is achiral. This is because it has a plane of symmetry, one half of its molecule being mirror image of the other half. As such, the compound represented by formula 9 11 or 12 is optically inactive. Such an optically inactive compound whose molecules are not chiral even though they contain two or more chiral center is known as meso compounds. As explained above, the molecule of such compounds are superimposable on their mirror images. Thus, tartaric acid exists in three forms: minus tartaric acid, positive tartaric acid formula 9 and 10, and mesotartaric acid formula 11 or 12. Although optically inactive, the mesotartaric acid represent a diastereomer of negative or positive tartaric acid. Fischer projection and flying wheel formula of three stereoisomer of tartaric acid are given below. Racemization. It has been stated earlier that an optically inactive mixture containing equal quantities of enantiomer of a substance is known as racemic mixture or racemate. It is denoted by using the prefix plus minus or DL or RS before the name of the compound. For example, a racemic mixture of lactic acid is denoted as plus minus lactic acid. Racemic mixture can be formed in one of the following three ways: synthesis of chiral compounds from achiral reactants, mixing of equal amounts of two enantiomer already described. Racemization. We will now consider the process of racemization and its mechanism. Racemization. The optically active compound into a racemic mixture containing equal amount of organic compounds and its enantiomer is known as racemization. Racemization can be brought about by one of the following methods depending upon the nature of the compound. By the action of heat, quite often an optically active enantiomer changes into a racemic mixture by the action of heat. For example, when positive tartaric acid is strongly heated with water, it gets converted into a mixture of racemic and mesotartaric acid by the action of chemical reagent. Racemization is also brought about by the presence of four resin substances, particularly acid and base, in the solution of an optically active substance. For example, addition of sodium hydroxide to positive or negative lactic acid leads to the formation of racemic mixture. Auto-racemization. In such cases, racemization takes place by merely keeping the substance at room temperature for some time. This is known as auto-racemization. For example, one any one of the enantiomer of dimethyl bromosuccinate changes into a racemic mixture on standing at room temperature. Mechanism of racemization. Different mechanisms have been developed for racemization of different type of compound, but in majority of cases racemization is believed to take place through the formation of some intermediate which is no longer chiral in nature as explained ahead. Acid catalyst racemization of an optically active aldehyde or ketone in which chiral carbon carries a hydrogen and is in alpha position with respect to carbonyl group take place through enolization. That is the intermediate form of an achiral enol. By tautomeric change, the enolic form being unstable reverts to the chiral keto form, but in doing so it produces positive or negative enantiomers in equal quantity and thus racemization takes place. This is shown ahead with the help of 3-methyl 2-pentanone. This is shown in this figure that positive keto form when 1H is added will give this compound given further, and minus H will again give this positive keto form. Same for enolic form and minus keto form, irrespective of whether the starting compound is positive or negative 3-methyl 2-pentanone. The final product is a racemic mixture since both the enantiomer are formed in equal quantities. Base catalyst racemization of negative lactic acid taking place through the formation of an achiral carbanion as shown below. The final product will be a racemic mixture whether we start with a negative or positive enantiomer of lactic acid. We will come across many examples of chemical reaction in the text such as SN1 reaction of alkyl halide discussed in chapter 9, which are accompanied by complete or partial racemization. Partial racemization means that one enantiomer may be formed in a larger amount than the other so that the mixture of the two will not be completely inactive. Resolution of racemic mixture. The process of separating of a racemic mixture into its enantiomer is called resolution. It is not easy to carry out resolution in actual practice. It is because enantiomers have identical physical and chemical properties which makes their separation from each other very difficult. Therefore, special methods have been introduced for this purpose. Mechanical separation. If the enantiomer of a substance exists in well-defined crystalline form, the separation can be done by hand pricking with the help of a magnifying lens and a pair of tweezers. For example, the enantiomer of sodium ammonium tartrate can be separated by this method. Limitation. This method have very limited application as very few enantiomeric substances exist in the form of mechanically separable crystals. The method is very laborious and time consuming. Biochemical separation. This method involves the use of microorganisms for bringing about a solution. If certain bacteria, yeast or molds are allowed to grow in a dilute solution of racemic modification, one of the enantiomer is separately consumed by the microorganism while the other is left behind. For example, when the mold Penicillium glaucum is allowed to grow in the solution of racemic ammonium tartrate, the mold completely destroys plus ammonium tartrate while negative ammonium tartrate is left practically unaffected. Limitation. The main disadvantage of this method is that one half of the material is destroyed during separation. As the separation is carried out only in dilute solution, the process is very slow and one small amount of material can be separated. Chemical separation. This is probably the best method of resolution. It involves the conversion of racemic mixture into a mixture of diastereomers of some other substances by reaction with an optically active reagent. Since diastereomers have different physical properties, the mixture of diastereomers can be easily separated from through fragmentation, crystallization, fraction fractional distillation, chromatography, etc. Each of the diastereomers is then suitably treated to generate a pure enantiomer of the original substance. For example, if a racemic mixture of positive or and negative lactic acid, single enantiomer of an optically active base say negative berusine, it would result in the formation of a mixture of two crystalline salts. The two salts formed would be negative berusine, positive lactate, and minus berusine minus lactate. While bricane part of these salts have the same configuration, in both cases the acid parts have non-superimposable mirror images configuration in two cases so that the two salts represent two diastereomers. As such, the crystal of two salts differ in their solubility and can be separated by fractional crystallization. One of the separation has been activated achieved reaction of each salt with hydrochloric acid would generate a free lactic acid in pure enantiomeric form. Plus minus lactic acid plus minus brucine will give minus brucine plus lactate plus minus brucine minus lactate can be separated by fractional crystallization. Minus brucine plus lactate plus HCl will give plus minus lactic acid get crystallized plus minus brucine and HCl. Minus brucine minus lactate plus HCl will give minus lactic acid plus brucine minus brucine HCl remains in the solution. Apart from the separation of racemic acid or bases by this method, it can also be employed for the separation of racemic alcohols, aldehydes, etc. by treating with suitable optically active reagents. Chromatography. These days, chromatography technique such as adsorption chromatography using optically active adsorbents, paper chromatography and gas chromatography are also being used for the solution. In adsorption chromatography, the solution of racemic mixture is a suitable solvent is passed through a column packed with optically active absorbent when differential adsorption of the enantiomer takes place. This is followed by elution with the suitable solvent to get each enantiomer separately. Asymmetric or enantioselective synthesis. It has been already pointed out that when a chiral compound is synthesized from a chiral compound, the product obtained is in the form of a racemic mixture. For example, propanoic acid in the presence of Br2 or phosphorus will give racemic mixture of plus and minus alpha bromopropanoic acid. The racemic mixture has then to be resolved in the enantiomers through method described on previous page. It is however found that if a chiral compound is prepared from a chiral compound under the influence of some optically active substance which is subsequently removed, the product formed is optically active. The method of directly preparing an optically active isomer from a chiral molecule under the influence of some other optically active substance is called asymmetric or enantioselective synthesis. It may be pointed out that even in asymmetric synthesis both the positive and negative enantiomers are formed, but one of these is obtained in predominating amount so that the product exhibits a net optical rotation. The following example illustrate the applicability of this process. First, synthesis of minus lactic acid. Lactic acid obtained by the direct reduction of pyruvic acid such is followed is found to be in the form of racemic modification. However, if pyruvic acid is first esterified with an optically active alcohol such as minus methyl alcohol and the ester formed is subjected to reduction and then hydrolysis, we get a product having excess of minus lactic acid. Pyruvic acid plus minus methylic alcohol will give minus methyl pyruvate. On reduction will give negative methyl lactate. On hydrolysis will give minus lactic acid as main product plus minus methyl alcohol. Synthesis of minus mandelic acid. Mandelic acid may be obtained in racemic form by the reaction of benzaldehyde with hydrogen cyanate formed by hydrolysis, but when the same synthesis is carried out in the presence of a enzyme emulsion like most other enzymes, it is also
optically active. Minus mandelic acid is found to be the main product. Benzaldehyde on reaction with HCl will give mandelic nitrate on hydrolysis will give minus mandelic acid main product obtained in the presence of emulsion. Most of the chiral compound found in nature such as alkaloids and protein are obtained in optically active form. This is because they are synthesized in nature under the influence of other optically active species. Inversion of configuration. Well done. Inversion. If an atom or group of atom directly attached to a stereogenic center is substituted by some other atom or group, the configuration of new compounds is sometimes found to be different from that of the original compound. It is known as inversion of configuration or optically inversion. This phenomena was first discovered by Walden and is therefore also known as Walden inversion. For example, when minus chlorosucinic acid is treated with aqueous potassium hydroxide, the product form is plus malic acid having a different configuration than the starting compound. Minus chlorosucinic acid when treated with aqueous KOH will give plus malic acid. Inversion of configuration when treated with aqueous KOH minus 2 bromo octane gives plus 2 octanol, which was a configuration opposite to that of minus 2 bromo octane. This that is minus 2 bromo octane when treated with OH negative will give plus 2 octanol. Inversion of configuration. It may be noted, however, the change in the configuration may or may not be accompanied by change in direction of rotation. Retention of configuration. If a compound containing a stereogenic center is converted into another without bring, breaking any of the bond with the stereogenic center, the product has the same configuration as the original compound. This means that the reaction proceeds with the retention of configuration. For example, minus 3 bromo 2 hydroxyl propanoic acid on reaction with Zn and HCl will give minus lactic acid, same configuration and its specification. Configuration: the arrangement in space of the atoms or group constituting a stereoisomer is called its configuration. For example, the configuration of the two enantiomers of lactic acid are 1 and 2 shown below. One of these configuration represent dextro or positive lactic acid while the other represent levo or negative lactic acid. Specification of configuration, DLN notation. We will state that one of the enantiomer of lactic acid have the configuration 1 while the other has the configuration 2 given above. We merely represent a two possible configuration of the enantiomers of lactic acid. What is not indicated is which configuration represent which isomers, that is which one of the two enantiomers positive or negative have the configuration 1 and which has the configuration 2. In other words, we do not know the actual or absolute configuration of each of two enantiomers. In the earlier days of the study of steriochemistry, it was not found possible to determine the absolute configuration of the compound. Fortunately, it is not found it is not always necessary to know the absolute configuration of an optically active compound. On the other hand, we are more interestingly in knowing the relative configuration of different compounds. For example, when an optically active compound undergoes a chemical reaction, we are merely interested in whether the configuration of reactants and its product are same or different, and not in their actual configuration. Relative configuration: standard reference compound to assign relative configuration to various optically active compounds and to indicate their relationship What was done was to choose a standard reference compound and fix its configuration arbitrarily as proposed by Emil Fischer. Made clear that the symbol D and L refers to the configuration and are quite different from the prefixes D and L read as dextro and levo, which refers to the direction of rotation. Positive glyceraldehyde was arbitrarily assigned the configuration 3, in which the OH group attached to chiral carbon is towards right and was given the symbol D. The minus enantiomer was assigned the configuration 4, in which the OH group attached to chiral carbon is towards left and was given the symbol L. The three directional and planar representation of two enantiomers of glyceraldehyde are shown. Reason for selecting glyceraldehyde as the standard. Glyceraldehyde was chosen as the standard mainly because of the following reason. First, it is the simplest carbohydrate and aldotriose, and its configuration could be easily related to those of the other carbohydrates, which are stereochemically very important compounds. Since glyceraldehyde contains very reactive functional groups, it could be converted into many other types of compounds. In this way, it could be configurationally related to a number of compounds. Absolute configuration. It was only in 1951 that by using X-ray diffraction studied Bijvoet was able to determine the absolute configuration of a compound, that is, the actual arrangement in space of the atoms or group constituting a particular stereoisomer. The first compound whose absolute configuration was determined was sodium rubidium salt of plus tartaric acid. Bijvoet found that positive tartaric acid actually has the same configuration which it was previously assumed to have on the basis of configurational relationship between glyceraldehyde and tartaric acid as discussed above. If the assumed configuration of positive tartaric acid was correct, the assumed configuration of the two enantiomers of glyceraldehyde must also be correct, as the configuration of all two compounds derived by correlation with glyceraldehyde must be correct once. Thus, relative configuration assumed to D negative glycolic acid, L negative lactic acid, carbox carbohydrates, and a large number of other compounds actually represent their absolute configuration. The absolute configuration of some simple but steriochemistry important compounds are given below in planar form. Limitations of DNL system of configuration. The system of designing the configuration as D and L is essentially referred upon based upon the configurational relationship to one or the other enantiomer of glyceraldehyde, but the procedure followed has certain limitation. It has been found that in some cases a given compound can be related by a sequence of reactions to a known compound having D configuration, but all the same time by another sequence of reactions. The given compound can also be related to the L enantiomers of the known compound. This led to an ambiguous situation where the same compound may be assigned either D or L configuration. It may, however, be pointed out that in case of carbohydrate and amino acids, certain conventions have been adopted, due to which the system of assigning D and L configuration is found very useful in this class of compounds. Rectus and semester or R and S sequence for specification of configuration. In view of the limitation of L and D system of configuration, can in Gold and Prelog suggested a very simple procedure of specifying a particular configuration of a substance in terms of prefix R and S. The procedure involved the following two steps. Step 1. the four atoms or group of atom bounded to a chiral. The four atoms or group of atom bounded to the chiral center are assigned a sequence of the priorities in accordance with a set of rules known as the sequence rules. Sequence rules. The sequence rules are as follows. Rule 1. If all the four atoms directly attached to the chiral center are different from one another, sequence of priorities is determined by their atomic number. The atom of highest atomic number get the highest priority, while the one with the lowest atomic number comes last in the order of priority. For example, in the compound 1 bromo 1 chloroethane, the four groups attached to the chiral carbon atom are CH3, HCl and Br. This sequence of priority will be given PrCl, CH3 then H. Similarly, the order of priorities of the group CH3OH NH2 and H is OH NH2 CH3H. If two isotopes of the same elements are involved, the isotopes with the higher mass number get higher priority. For example, out of hydrogen and deuterium gets higher priority. Rule 2. If the first atom of two or more groups attached to the chiral center have the same atomic number, the relative priority may be fixed by comparing the next atom in the group. If even this does not solve the problem, the comparison may be extended and further to the next atom and so on. For example, in secondary butyl alcohol, the relative priority of CH3 and C2H5 are discussed as follows. Each of these groups is linked to the chiral center through the same atom, that is carbon. The next atom is CH3 and H and H, while in C2H5 they are C, H and H. Carbon has a higher atomic number than hydrogen. C2H5 get higher priority than CH3. CH3, C2H5, CHOH, CH3. Therefore, the complete sequence of priority is OH, CH3, CH2, CH3H. If the group contain a double or triple bond between two atoms, it is treated as equivalent to two single bond or three single bonds between the two atoms. In other words, each pi bond is supposed to be broken and atom at each end of the pi bond are duplicated. While doing so, two imaginary atoms are attached for each pi bond broken. For instance, C double bond X is treated as equivalent to C is attached to X and also to another X on which another C is attached. Here the X and C, which are in circle, they are imaginary atoms added due to the breaking of pi bond. Thus it is considered that the group C double bond X contain two atoms of X attached to carbon. Since C triple bond Y is treated as equivalent to C is on C, two Y are attached in circle and it is also attached to one Y on which two C are attached, which are in circle. Therefore, the group C triple bond X Y is considered to contain three atoms of Y attached to carbon. To take a specific example, in the group CH double bond O, next atom to carbon are equivalent to OO and H. This is CH double bond O is treated as equivalent to this. That is, there are two atoms of O and one atom of H attached to carbon. Therefore, if we compare the groups CHO and CH2OH, the former get higher priority as in it the atom get the next to carbon are OO and H, while the in CH2OH they are OH and H. comparison of the priority of some typical groups. Let us compare the relative priority of vinyl CH double bond CH2 and isopropyl groups. In isopropyl groups, the first carbon is attached to two carbons and a hydrogen. In vinyl group also, the first carbon is treated as linked to two carbons and one hydrogen. But in vinyl groups, the second carbon is further attached to one carbon and two hydrogens. On the other hand, in isopropyl, the second carbon is attached to only one hydrogen. Therefore, vinyl group get priority over isopropyl group. Similarly, phenyl groups get priority over acetylenic group. Phenyl groups is considered as if it has one of the calcular structure. This is the benzene is can be written as this another structure which is also benzene treated as equivalent to this given structure. Acetylenic group C triple bond CH is equivalent to this given structure. In both, the first carbon is taken as attached to three carbons. In phenyl, two of the three carbons attached to first carbon are further attached to two carbons and a hydrogen, while the three is a duplicate carbon. In acetylenic group, only one of the three carbon attached to first carbon is further attached to two carbons and a hydrogen, while the other two are duplicate carbons. Therefore, phenyl group get priority over acetylenic group. It is very evident that phenyl or acetylenic group would get priority over vinyl or isopropyl group. This is because in phenyl or acetylenic group, the first carbon is attached to three carbons, while in vinyl or isopropyl, the first carbon is attached to only two carbons. Thus, the order of priority of these given groups would be C6H5, then C triple bond CH, then CH double bond CH2, then CH3CH CH3, which is isopropano. Relative priority of given common groups. To sum up the given discussion on the determination of priorities of different groups, we give below the relative priorities of common groups in increasing order of priority. These are the priority groups in the increasing order. Second, step 2. Having decided the sequence of priority, the molecule is imagined to be in the position where the groups are of lower priority is directed away from us. Now we look in the arrangement of remaining groups in decreasing order of their priority. Highest or number 1 downwards. If in doing so the I traveler in a clockwise direction, the configuration is specified as R. Latin rectus means right. If on the other side, if the hand travels in anti-clockwise direction, the configuration is specified as S. Latin sinister means left. Configuration on the basis of projection formula. While assigning configuration to a stereoisomer on the basis of projection formula, two kinds of situation may arise. First, if the groups of lowest priority is bounded vertically, that is pointing away from the observer, the configuration is assigned by following exactly the same pro- procedure as in case of a three-dimensional formula. For example, in the structure given below, the sequence of priority is Cl, then benzene, then CH double bond CH2, then H. The given group of lowest priority, that is H, is bounded vertically, that is pointing away from us. The movement of the eye is moved from Cl to benzene to CH double bond CH2 is anti-clockwise, therefore configuration is S. Second, if the group of lowest priority is bounded horizontally, that is pointing towards the observer, an additional step is required. In such cases, the given formula is converted into another equivalent projection formula by making two interchange so that atoms or group of lowest priority is placed vertically downwards or upwards. Then the configuration is assigned by following the usual procedure. For example, assignment of a configuration to the given isomer of 2-butanol. Here, 2-butanol structure is given. First interchange H and OH. Then we will get this. Second interchange, when interchange H and CH2 CH3, we will get this. The sequence of priority is OH CH2 CH3 CH3 H. After the second interchange, H is bounded vertically in the projection formula. In moving from OH to CH to CH3 to CH3, the I travels in anticlockwise direction, therefore configuration is S. Third, assigning of configuration to the given isomers of 2 aminopropanol. 2-aminopropanol is given. First interchange, when we interchange H and NH2, we will get this. Second interchange, we interchange NH2 and CH3, we will get this structure. Sequence of priority is NH2 CHO CH3H. Configuration is R. It may be recalled that if we carry out two interchange of the group attached to chiral carbon, the configuration remain equivalent to the original configuration. Configuration of compounds containing more than one chiral atom. In such cases, the configuration about each chiral center is ascertained separately. The specification of each atom along with its number is then prefixed before the name of compound as illustrated below. Let us consider one of the form of tartaric acid given on the right hand side. Each chiral center carbon 2 and 3 in this molecule have the same set of four groups attached to it, that is COH, HOH and CHOH. COOH. The sequence of priority of these groups is OH, COOH, CHOH, COOH, and H. The configuration around C2 may be assigned as follows. Since the I has to travel clockwise in moving from OH to COOH to CHOH, C double bond H, the configuration around C2 is R. Let us now assign configuration to the compound. Each of carbon atom 2 and 3 has the groups CH3HCl and CHCl CH3 attached to it. The order of priority of groups is Cl, CHCl, CH3, CH3 and H. Configuration at 2C can be known as follows, which is shown in this diagram. Here configuration is S. Configuration as C3C can be obtained as follows. It is shown in this diagram. Here configuration is R. Hence the configuration of the above compound is 2S and 3R. Useful shortcuts for assigning configuration to Fisher projection formula. Decide the sequence of priority of the four atoms or group attached to the chiral carbon. Determine the configuration without making any interchange in the given projection formula. If the atom or group of the lowest priority is bounded vertical, either upwards or downwards in the projection formula, the configuration determined as above gives the actual configuration. If the atom or groups of lowest priority is bounded horizontally, either left or right in the projection formula, changes the configuration obtained above from R to S or vice versa to get the actual configuration. For example, this figure shows without making any interchange the configuration obtained is S. Since the atom of lowest priority, that is H, is bounded vertically, this represents the actual configuration. The second, without making any interchange, the configuration obtained is R. Since the atom of lowest priority, that is H, is bounded horizontally in the projection formula, changes R to S. Therefore, without making any interchange, the configuration obtained is S. Since the atom of lowest priority, that is H, is bounded horizontally in the projection formula, changes S to R. Therefore, actual configuration is R. Geometrical isomerism hindered rotation around carbon-carbon double bond. Geometrical isomerism and its cause. Geometrical isomerism is a type of stereoisomerism which is exhibited by certain compounds containing double bond and arises due to hindered rotation about the double bond. We will first discuss geometrical isomerism in compounds containing carbon-carbon double bond and then consider other type of compounds which also exhibit geometrical isomerism. A carbon-carbon double bond consists of a sigma and a pi bond, while the sigma bond is formed by the overlap of sp2 hybridized orbital of two carbon atoms along the internuclear axis. Pi bond is formed by size-weight overlapping of unhybridized p orbital of the two carbon atom above and below the plane of atom. Because of this type of overlapping, rotation around the carbon-carbon double bond is strongly hindered and can take place only if pi bond breaks, but this would require about 284 kilojoule of energy per mole, which is not available to the molecules at room temperature due to hindered rotation around carbon-carbon double bond. The relative position of groups attached to doubly bonded carbon atom get fixed. As a result, several higher alkanes and other substituted products can exist in two distinct isomeric forms which further differ from each other in the relative distribution of groups in space around the double bond. For example, malic acid and fumaric acid affords a very well known example of compounds which exist in a geometrically isomer form as shown below. Malic acid and fumic acid structures are given. These two isomers are like one another with respect to which atoms are attached to which other atoms but differs from each other in the relative arrangement of atom in space. In malic acid, the two carboxylic groups lies on the same side of the molecule, while in fumic acid the two carboxylic groups lies in opposite sides. Such isomers which have the same structural formula but differs in relative practical arrangement of atoms about the double bond are called geometrical isomers, and the phenomena is known as geometrical isomerism. It is obvious that geometrical isomerism represents a type of stereoisomerism, since the stereoisomers, which are not mirror images of each other, are called diastereomers. Geometrical isomerism can also be regarded as diastereomers. It may also be pointed out that in case of optical and geometrical isomers, the different structures of optical and geometrical isomers cannot be interconverted except by breaking and making of bonds. As such, these two types of stereoisomers are also collectively known as conformational isomers. Condition for geometrical isomers. There are two necessary conditions for geometrical isomers. These are: first, the molecule must contain a carbon-carbon double bond. The rotation around which is strongly hindered. Each of the two doubly bonded atoms should have two unlike groups attached to it, as for instance ABC is equal to CAB. The formula ABC is equal to CAB can all have two arrangements in space which represent the geometrical isomers as shown below. First shows similar groups on same side of the double bond. Second shows similar group on opposite side of double bond. Nomenclature of geometrical isomers. Cis and trans system. The method originally used for denoting the configuration of geometrical isomers is known as a cis-trans system. In this system, the name of the geometrical isomers have different configuration as distinct by using the prefix cis, which means on the same side, and trans, which means across before the name of the compound. The prefix cis is used when similar groups are on the same side of the molecule, while the prefix trans is used when similar groups are on opposite sides as illustrated below. Limitations of cis and trans system of nomenclature. The cis and trans system of nomenclature of geometrical isomers is not universally applicable. It cannot be employed in case of compounds where all the four substituents attached to the two doubly bonded carbon atoms are different from each other, that is ABC is equal to CED. For example, let us consider the following compound. Here we can see that I and Cl are cis to each other, but we can also equally well say that Br and Cl are trans to each other. Therefore, it becomes difficult to name such a system either as cis or trans isomers. E and Z system of nomenclature. In view of the limitation of cis and trans system, a more general system of nomenclature of geometrical isomers known as E and Z system is now being adopted. EZ system is based upon the sequence rule originally developed by Can, Prelog and Ingold for R and S system of specifically configuration of optical isomers. Please refer to section R and S system for specifying the configuration of geometrical isomers as E or Z. The following rules are followed. First, the two atoms or group attached to each carbon of the double bond are assigned a higher or lower priority according to the priority sequence rule of R and S system of optical isomers. Second, if the higher priority atom or group of each carbon of the double bond are on the same side, the configuration is designed as Z from the Greek word Jusamen means together. On the other hand, if the atoms or group of higher priority are on the opposite side, the configuration is termed as E from the Greek word Intigen means across. Thus, we have these are the structures shown for E and Z. It may be noted that the most of the compounds that we would normally designate cis are designated Z. Similarly, most of the compounds which are designated trans are designated E. Nomenclature of compound containing more than one double bond. In a compound contain two or more double bonds across which geometrical isomers is possible. E and Z designations are given to each double bond. Determination of configuration of geometrical isomers. The following method can be employed for determination of configuration of geometrical isomers. The following methods can be employed for determining the configuration of geometrical isomers. First, from the dipole moment. Determination of the dipole moment of a pair of geometrical isomers can be quite helpful in designating a particular isomer as cis or trans. For instance, in case of compounds of the type ABC is equal to CAB, the net dipole moment of the trans isomers is expected to be zero. This is because the similar groups are on the opposite side of the molecule and therefore the bond polarities cancel out each other. In contrast, the bond polarities are not cancelled in case of cis isomers and therefore it has a definite dipole moment. Thus, cis to butene should have a small dipole moment while the dipole moment of trans to butene should be zero. The following experimental data goes to support the above prediction. This shows the cis 1 to dichloroethene for dipole moment for this is equal to 1.85 d. Trans 1 to dichloroethane, the dipole moment for this is equal to 0. Cis 1 to dibromoethane, dipole moment is equal to 1.35 d. Trans 1 to dibromoethane, for this dipole moment is equal to 0. Second, from boiling points. In general, cis isomers have highest boiling point than trans isomers. This is evidently because of the higher polarities and higher dipole moment of cis isomers, which lead to greater intermolecular attraction. For example, the boiling point of cis 2 butene is 277 Kelvin, while that of trans isomers is 274 Kelvin. At the structure of cis 2 butene, boiling point 277 Kelvin and trans to butene boiling point 274 Kelvin is given. From melting point, generally speaking, trans isomers have higher melting point than cis isomers. This is because trans isomers are more symmetrical and can be more closely packed in the crystal structure. For example, malic acid, which is trans melting point is 403 Kelvin, and fumaric acid trans melting point is 575 Kelvin. From the formation of ring compound, sometimes it is possible to distinguish between both two geometrical isomers by chemical reactions which lead to the formation of rings. 6 isomer is likely to undergo ring closely much more readily than the trans isomers. For example, malic acid sits from loose water when heated at 423 Kelvin to form malic anhydride ring compound. On the other hand, fumaric acid transform does not give the anhydride at this temperature. Malic acid cis form will give at 423 Kelvin will give malic anhydride ring compound. Malic acid will give no reaction at 423 Kelvin. This transform form of malic acid at 423 Kelvin will give no reaction. Geometrical isomerism in compounds other than alkene. Geometrical isomerism can also exhibit by compounds in the molecules of which there may be hindered rotation due to some other reason than the presence of carbon-carbon double bonds. Thus, geometrical isomers is also shown by compounds having carbon-nitrogen double bond, oxime, nitrogen-nitrogen double bond, azo compounds, and even some cyclic compounds which do not contain any double bond as discussed below. First, geometrical isomer in oximes. Oximes are the compound formed by reaction between aldehyde or ketones and hydroxylamine. This is aldehydes or ketone plus NH2OH will give C double bond NOH. For example, acetaldehyde on reaction with NH2OH will give acetaldoxide plus H2O. Similarly, another compound C6H5C double bond OCH3 plus NH2OH will give this compound here the double bond O. Here O will be replaced by NOH plus H2O. Oxime exhibit geometrical isomerism due to hindered rotation around carbon nitrogen double bond, while the doubly bonded nitrogen carries only OH group attached to it. The doubly bonded carbon must have two unlike groups attached to it for geometrical isomerism to be possible. For example, these structures give geometrical isomerism of acetaldoxime. The configuration of geometrical isomers of oximes are usually denoted by prefix syn syn and anti instead of cis and trans respectively. In case of ald oximes, the isomer is named as syn if OH group attached to nitrogen is on the same side as attached to carbon. If the OH group attached to nitrogen is on the opposite side to hydrogen, the isomer is called anti. In case of ketoxime, the isomer is named as syn if the OH group attached to nitrogen is on the same side as the group attached to carbon, which comes first in the name of compound. If they are on the opposite sides, the name is anti. Second, geometrical isomerism in alicyclic compounds. There are many substituted alicyclic compounds which shows geometrical isomerism. This is because the presence of a ring can also prevent rotation around carbon-carbon single bond. Therefore, geometrical isomers become possible if there are two carbon on a ring, each of which is attached to two unlike groups. These two carbon may or may not be adjacent to each other. For example, dimethyl cyclopropane exists in two geometrical forms, one in which the two methyl groups are on the same side of the ring and the other in which the two are on the opposite side of the ring as shown below. This figure shows cis dimethyl cyclopropane and trans dimethyl cyclopropane. Similarly, cyclobutane 1,3-dicarboxylic acid and cyclopentane 1,2-diol also exhibit the geometrical isomerism. As shown in these figures shows cis cyclobutane 1,2-dicarboxylic acid, trans cyclobutane 1,2-dicarboxylic acid, and cis cyclopentane 1,2-diol and trans cyclopentane 1,2-diol. It may be pointed out that E and Z nomenclature is not used for cyclic configuration. compounds. Conformations. It is well known that a single or sigma bond between two atoms is formed by the overlap of their orbital along the internuclear axis. The electron distribution of sigma bond thus formed is therefore symmetrical around the axis as shown in figure 2.12. 1 to 4. A single bond between sp3 hybridized orbital of two carbon atoms. Due to its axial symmetry, the single bond allows freedom of rotation about it. As a result of this, the molecule of a compound can have different relative arrangement of their atom in space, which can be converted on one into the other by rotation around the single bond. Such arrangement in space of the atoms in a molecule that can be readily interconverted by rotation around single bond and cause conformation or conformational isomers. The existence of different conformations of the compound con- constitutes a special type of stereoisomerism. We will discuss some aspects of this phenomena which reference to alkanes and cycloalkanes. Conformation of ethane. Ethane is the simple molecule for which an infinite number of conformations are possible. The central bond in the molecule of ethane is a single bond between two carbon atoms, each of which is further linked to three hydrogen atoms. If one of the carbon atom of ethane is allowed to rotate around the central bond while the other is held still, a very large number of arrangements of hydrogens of the central bond while the other arrangements of hydrogen of one carbon with respect to the hydrogens of other carbon can be obtained. The basic structure of the molecule and various bond length and bond angle, however, remain the same in all their arrangement or configuration. Of the infinite number of possible configuration of ethane, two conformation represent extremes. These are called eclipsed conformation and staggered conformation. In the eclipsed conformation, the hydrogen of one carbon are directly behind those of the other. In the staggered configuration, the hydrogen of two carbon atoms are staggered with respect to one another. Representation of configuration. Since it is not very convenient to represent three-dimensional formula on paper, certain conventions have been adopted for projecting the conformation on paper. The two commonly used methods are as follows. First, Sahor formula or Anderum formula. In this representation, the molecule is viewed slightly from above and from the right and then projected on the paper. The bond between the two carbon atoms is drawn diagonally and of a relatively greater length for the sake of clarity. The lower left hand carbon is taken as front carbon and the upper right hand carbon as the back carbon. The three atoms and groups attached to each carbon are shown tetrahedrally in space. The Sahor's representation of eclipse and staggered configuration of ethane are shown in figure 2.30. This shows the Sahor's representation of eclipsed and staggered configuration of ethane. Newman projection formula. Newman devised a very simple method of projection, a three-dimensional formula on paper, which are known as Newman projection. In this formula, the molecule is viewed from the front. The carbon atom near to the eye is represented by a point or dot, and the three atoms or groups are shown attached to it by three lines at the angle of 120 to each other. The carbon atom further from the eye is represented by a circle, and three atoms or groups are shown attached to it by shorter lines ending at the circumference of the circle at an angle of 120 to each other. Newman projection for eclipsed and staggered configuration of ethane are shown in figure 2.14. This shows the Newman projection for the configuration of ethane. Difference between conformation and configuration. Conformation, as stated above, conformations are three-dimensional arrangements in space of the atoms in a molecule that can be interconverted merely by rotating about single bonds. For example, figure 3.13 depicted two such arrangements known as eclipsed and staggered conformation of ethane, which are readily interconvertible by rotation around carbon-carbon single bond. Configuration. As already studied, configuration are three-dimensional arrangements in space of the atom in a molecule that cannot be interconverted merely by rotation about a bond. For example, the conformation of minus lactic acid and positive lactic acid, which are not interconvertible by rotation about the bonds, are shown in figure 2.15. This shows the conformation of minus and positive lactic acid. In the light of above definition, the main points of difference between conformation and configuration may be summed up as follows. Conformation. First, these are three-dimensional arrangements in space of the atom in the molecule which are interconvertible by rotation around a single bond. Configuration are three-dimensional arrangements in space of an atom in the molecule which are not interconvertible by rotation around a bond. Conformation their interconversion does not require any breaking and making of bond. In confirmation, interconversion is possible only through breaking and making of bonds. Confirmation existence led to the phenomena of conformational isomerism. Configuration existence is involved in the phenomena of geometrical and optical isomerism, which are also collectively known as conformational isomerism. In confirmation, since confirmations are readily interconvertible, they cannot be isolated from each other. As such, confirmation isomerism exists only as a mixture of different confirmation. Since configuration are not easily convertible interconvertible, they can be isolated from each other and stored as pure substances. As such, conformational isomerism can exist as pure individual substances. Conformational analysis of ethane. It has been stated earlier that a single bond allows freedom of rotation around it. However, it must be pointed out that rotation around the single bond is not completely free. It is If it were so, the potential energy for different conformations of a compound should have been the same, but in actual practice, the potential energy of the molecule changes somewhat with the rotation around the CC single bond. The study of energy changes which occur in a molecule due to rotation around CC single bond is known as conformational analysis. Let us first study the energy change taking place in ethane. The potential energy of an ethane molecule is minimum for the staggered configuration conformation, increases with rotation and become maximum for eclipsed conformation. The difference between the two extreme conformation being 12.55 kilojoule per mole. This difference in energy constitutes an energy barrier to rotation around the single bond. The energy barrier to rotation in ethane is said to be due to torsional strain, and the energy required to rotate the ethane molecule about the carbon-carbon bond is called torsional energy. These terms are explained a little later in session 2.24. This figure shows the changes in potential energy during rotation about carbon-carbon single bond of ethane. The energy barrier to rotation described above is, however, not large enough to predict rotation altogether. Even at ordinary temperature, the molecule possesses sufficient thermal or kinetic energy to overcome the energy barrier through effective collision, and thus the conformation keep on changing from one to the other. On other hand, rotation around the single bond can still takes place nearly freely, being only slightly restricted by the energy barrier. As such, it is not possible to separate a different conformation of ethane. It is quite obvious, however, that at any moment most of the ethane molecules would exist in staggered conformation due to its minimum energy and therefore maximum stability. In other words, any molecule spend most of its time in the staggered conformation, which is the most stable conformation. Conformation analysis of N-butane. The molecule of N-butane, which may be considered as a desubstituted ethane, is somewhat more complex for conformational studies. If we consider the rotation only around the single bond between the two inner carbon atoms C2 and C3 of N-butane, we have a molecular similar to ethane but with the bulky group, that is methyl group, in the presence of hydrogen atom of each carbon. In contrast with ethane, and butane can have several different staggered and eclipsed conformation due to the presence of methyl group. Four of the important configurations are anti-eclipsed, gauge, and fully eclipsed. These are shown in figure 2.18. First shows anti, second shows eclipsed, third shows gauge, fourth shows fully eclipsed, fifth shows gauge, and sixth shows eclipsed. When these are rotated by 60 degree each, they will give change the configuration. The figure shows the important conformation of N-butane. The anti-conformation one is an es- extreme staggered conformation in which the methyl group are as apart as possible. If the angle of rotation around C2 C3 single bond is assumed to be 0, this conformation and one of the C2 or C3 carbon atom is rotated through an angle of 60 degree and eclipsed conformation to result. In this conformation, the methyl group attached to one carbon is not at the back of the methyl group attached to other carbon but is at the back of hydrogen atom to this carbon. Rotating at another 60 degree leads to another staggered conformation called gauge conformation third, in which the two methyl groups are only 60 degree apart. Further, rotating by 60 degree gives rise to fully eclipsed conformation in which the two methyl groups are at the back of each other. On further successive rotation by 60 degree, we pass through another gauge conformation fifth and another eclipsed conformation sixth, and finally arise at the anti-conformation. Again, on completion of 360 degree, the difference in energy content between conformation 1 and 4th is about 18.4 kilojoule per mole, about between 1 and 2 or 6th about 14.6 kilojoule per mole, and between 1 and third or fifth only about 3.8 kilojoule per mole, as shown in figure 2.19. This figure shows the change in potential energy during rotation about C2 C3 single bond of N-butane. Therefore, the order of stability of different conformation of N-butane is anti-gauge, eclipsed, fully eclipsed. It is apparent that due to a very small difference in their energy, anti-conformation is only slightly more stable than gauge conformation. The difference in energy of anti and gauge forms is due to steric strain, which is discussed in session 3.24. It can be easily seen that the rotation about carbon-carbon single bond in N-butane is again nearly free and the different conformation cannot be isolated at any time. N-butane consists mainly of an equilibrium mixture of anti and gauge conformation, with the anti conformation having the highest percentage, about 67%, as 295 Kelvin. Conformation of cyclohexane. We have so far studied the conformation of open chain compounds. Let us now have a look at the conformation of cycloalkanes by considering the case of cyclohexane. Cyclohexane is a multiplanar or puckered ring compound in which carbon atoms are in sp3 hybridized state and all the bond angles are equal to normal tetrahedral angle. Of the various possible conformation of cyclohexane, the two most important conformation are chain conformation and bond conformation. First, chain conformation. This is the most stable and therefore the most predictly conformation of cyclohexane. In this conformation, all the bond angles are tetrahedral and all the CH bonds on adjacent carbon atoms are in a staggered position. At the same time, there is no steric inference or dipole-dipole interaction between the non-bounded atoms. Thus, this conformation is essentially free of strain and has minimum energy. In other words, this is most stable conformation of an hexane. This figure shows the chain conformation of cyclohexane. Second, boat conformation. This is the second most important conformation of cyclohexane and is depicted in figure 2.22. As in chain conformation, there is no angle strain in the boat conformation since all the bond angles in it are tetrahedral, but in boat conformation, the hydrogen on 4 of the carbons C2, C3, C5 and C6 are eclipsed. As a result, there is a considerable torsional strain. This figure shows the boat conformation of cyclohexane. Third, twist boat or skew boat conformation. Let us consider a model of boat conformation of cyclohexane as shown in figure 2.23a. Suppose we held C2 and C3 in one hand and C4 and C5 in the other and twist the molecule so that C3 and C6 go down while C2 and C5 comes up. It will be noted that during this twisting the flagpole hydrogen on C1 and C4 marked HA and HB in the figure move apart, and at the same time two hydrogens on C3 and C6 marked HC and HD in the figure begin to move more closely together. In this way, we get another conformation called a twist bond or skew bond conformation, in which the distance between HA and HB is equal to that between HC and HD. It is quite evident that in this conformation the van der Waals strain between flagpole hydrogen is minimum. At the same time, the torsional strain on C2 and C3, C5 and C6 is also appreciably reduced. As such, the twist bond conformation is more stable than the boat conformation by about 6.7 kJ per mole, although it is still less stable than chain conformation by 23 kJ per mole. This figure shows the twisting of boat conformation. Fourth, half chain conformation. In between the chain conformation and twist bond conformation lies yet another conformation known as half chain conformation. It has both angle and torsional strain and has about 46 kJ per mole higher energy than chair form. In fact, it represents merely a transition state conformation. Energy relationship between different conformations. The energy relationship between different conformation of cyclohexane has been shown in figure 2.25. It must be pointed out that the energy difference between any two conformation is too small to permit their isolation. It is evident that the order of relative stability of different conformation of cyclohexane is chain conformation, then twist boat conformation, then boat conformation, then half chain conformation, equatorial and axial bond in cyclohexane. Since the chain conformation is the most preferred and the most important conformation of cyclohexane, let us examine it a little more closely. Although the cyclohexane ring is not flat, we can imagine an average or general plane of the ring. Now, if we consider the position of various hydrogen atom in the chain conformation, we find that there are two different kind of hydrogens. So 6 of the hydrogen mark He in figure 2.26 point sideways along the general plane of the ring and are called equatorial hydrogen because they are situated along the general plane of equatorial band of the molecule. The 6 hydrogen marked Ha in two groups of 3 each lies above or below the general plane and point along an axis perpendicular to ring. These are called axial hydrogens. The bond by which an equatorial hydrogen is held is called equatorial bond, and the bond by which axial hydrogen is held is called axial bond. This is one equatorial and one axial bond on each carbon in the chain conformation of cyclohexane. This figure shows the equatorial and axial bonds in cyclohexane. It is interesting to note that axial and equatorial hydrogen in cyclohexane are interchange their position. This is because the chain conformation of cyclohexane is flexible and one chain conformation can change into another conformation by process called as ring inversion, ring flipping. As this happens, all hydrogen originally axial become equatorial and vice versa, but one chain conformation is perfectly equivalent to the other and they cannot be distinguished from each other. Conformation of monosubstituted cyclohexane derivatives, as the two bonds of each carbon of cyclohexane ring are not equivalent in position. A mono-substituted cyclohexane derivative should exist in two isomeric form according as the substituent group in an equatorial and axial position. Such equatorial and axial conformation of a substituted cyclohexane can interconvert in each other at room temperature by ring flipping, but they are not equivalent to each other in energy. The conformation having the substituent in equatorial position have slightly lesser energy than the other and is somewhat more stable. The reason for this can be understood by constructing their model. It can be seen that the model that a substitution of an axial hydrogen by bigger atom or group leads to considerable crowding between this substituent and the two axial hydrogens on the same side of the molecule. The interaction resulting from such crowding of axial atoms or group is called 1,3 diaxial interaction. To illustrate the operation of such interaction, let us consider methyl cyclohexane. Figure 2.27 shows the two possible chain conformation of methyl cyclohexane, one having methyl group in an axial position and the other having a group in equatorial position. This figure shows two possible chain conformation of methyl cyclohexane. It can be seen that one of the hydrogen of axial methyl group on C1 is more closer to the axial hydrogen on C3 and C5, but there is no such significant crowding when the methyl group is in equatorial position. In other words, axial methyl group is more crowded than the equatorial methyl. The resulting 1,3 diaxial interaction is responsible for lesser stability of axial conformation than the equatorial conformation, the difference in the relative steady of the two being 7.5 kJ per mole. Since the difference of 7.5 kJ per mole of energy between axial and equatorial conformation of methyl cyclohexane is due to 1,3 dimethyl diaxial interaction between one methyl group and two hydrogens, it is reasonable to accept that 1,3 diaxial interaction between each axial hydrogens and methyl group lead to difference of 3.75 kJ per mole. This can enable us to predict the relative stability of the various conformation of substituted cycloalkanes having more than one methyl group. As stated above, the equatorial methyl cyclohexane and axial methyl cyclohexane can interconvert into each other readily and exist in equilibrium with each other, but at room temperature 95% of the molecule of methyl cyclohexane are those having axial methyl groups. This is apparently due to less energy or greater stability in case of equatorial methyl group. Conversion of Fisher projection formula into Sahor's formula and Newman projection formula. In conclusion of the discussion on the stereochemistry of organic compounds, we may point out an interesting drawback of Fisher projection formula of diastereomers having two chiral carbon atom. The Fisher projection formula of such compounds correspond to the less stable eclipsed conformation involving maximum crowding between the substituted
group attached to the two chiral carbon atom, but actually the molecules acquire the shape which correspond to the staggered form in which the substituents are as far apart from each other as possible. Therefore, the best way of representing such molecules is to depict them in their staggered form by mean of Sahor's formula or Newman projection formula as explained below. First, conversion of Fisher projection formula into Sahor's formula. This involves two steps as given below. First, write the Fisher projection formula and change it into the equivalent eclipsed representation in terms of Sahor's formula. Second, rotate one of the chiral carbon atom by an angle of 180 degree around the bond between the two chiral carbon to get the Sahor's representation of staggered form. For example, let us convert 2s3r 3-bromobutane 2-ol from Fisher projection formula to Sahor's formula. We took this structure in Fisher projection, then it is given in Sahor's projection. Rotate C3 through 180 degree will give Sahor's representation. Conversion of Fisher projection formula into Newman projection formula. This also involves a similar procedure in which the Fisher projection formula is first translated into the equivalent eclipsed form in terms of Newman projection formula. The later is then changed into the staggered form by rotating through an angle of 180 degree around the bond between the two chiral carbon. For example, this figure shows 2s3r 3-bromobutane 2-ol in Fisher projection. Then the same is shown in Newman projection. When rotated C3 through 180 degree, we will get another Newman projection. So here our chapter is completed. Thank you.